Hello everyone, I'm the Electronic Sidekick. Let's talk about voltage dividers. Let's start with how to calculate them and then get into the gotchas of the actual implementation. What we've got on the screen is a voltage divider. It's comprised of two resistors in series with a voltage being applied to one of the resistors. The other resistor is attached to ground, and we're tapping a voltage off the midpoint of the two resistors. As far as the voltage divider equation is concerned, the resistor with the voltage applied is always R1, and the resistor that is attached to ground is always R2. And the equation that relates all of this together is super simple. It is the output voltage is equal to the input voltage, all multiplied by R2 divided by R1 plus R2. Let's throw some values in here and work through an example. So we'll set R1 equal to 90K, R2 equals to 10K, and we'll apply a 10 volts to V in. Now let's go back to our equation. Let's substitute for R1, that puts 90K there. Let's substitute for R2, that's putting that 10K in, just like that, and V in is our 10 volts. Awesome. Now it's just arithmetic and let's solve. Let's simplify the bottom, add those two together to give us 100K on the bottom. Now let's simplify the divisor. There we go, 1/10, and multiply that by the 10 volts, and that gives us 1 volt for our output voltage. Here's another example. We've got another resistor divider. Let's pause the video for just a second and try to figure out which one of these resistors is going to be R1 and which one's R2. Let's start by finding V in and V out. If you remember, V in is where the voltage is applied. So let's look at our voltage source, which is this battery up here. The batteries are, the positive of a battery is indicated by the long line, as well as I have it notated with the plus over here. So that means this left side is going to be our V in, and the output, V out of a voltage divider, is between the two resistors. So if you remember, R1 is always the most positive resistor, so it's going to be the one here on the left. That leaves us with R2 here on the right. Now let's get some values. So for R1 and R2, we'll assign those 100K, and we'll have a 12 volt input voltage. Go ahead and pause the video and try to solve this on your own. Awesome. So let's remember what the equation for a voltage divider is. Let's go ahead and plug in R1 and R2, and let's throw in the 12 volts for V in. Awesome. Back to arithmetic. Let's simplify the bottom, make that 200K, solve the division. That's 1/2 times our 12 volts is 6 volts, and that is the solution for this particular voltage divider. And here is the voltage divider from the first example, but we just made one change. We added a 10 kilo ohm resistance load to V out. So if you remember in the first example, V out was equal to 1 volt. And if V out is 1 volt, then this 10K load will have 0.1 milliamps or 100 microamps flowing through it, which is not a lot in the scheme of things. But let's see what happens to the output voltage now that we've loaded it. So load and R2 are in parallel to each other, so we can go ahead and combine those. That gives us 5K equivalent parallel resistance for R2. So let's go ahead and fill out our equation. That's already done, and we can just go ahead and solve that. And that gives us an V out of 0.526 volts. So almost half of what the unloaded resistor divider network was. So what that means is this voltage divider networks are a high impedance voltage source. So V out is a voltage source. You're going to feed that into something. But it is a high impedance source. It's actually got an impedance of 90K. And what that means is if you start pulling much current at all out of it, you're going to lose your voltage very, very quickly. Okay, let's go back and change the 10K load up to 6 mega ohms. And let's do that to make it more representative of like an op amp or comparator, something you would actually feed a voltage divider output into, something with a high impedance input. So now we've got our load of 6 mega ohms in parallel with R2, which is 10K. Let's put those in parallel. Great. Now, that gives us an R2 of 9.983 kilo ohms, much closer to 10K than the 5K of the past. So let's go ahead and throw that in the equation shown above, and then let's solve that, and that gives us 0.998 volts. That is a heck of a lot closer to the optimum 1 volt that was designed. What does this mean? It means that voltage dividers are a high impedance voltage source. It means you feed them into something that is also a high impedance input, something that's not going to draw current. You wouldn't want to use this, a voltage divider, off of a 10 volt rail to try to drive a 3.3 volt chip of some kind that's going to draw actual current. Because as the current of the chip changes, the voltage is going to change that's applied to it. It's messy. It doesn't work. Use it only into high impedance inputs of op amps, comparators, microcontroller inputs. That's where you want to use a voltage divider. Now let's look at another consideration when designing voltage dividers, and that's the amount of current they consume. So if we look at this voltage divider here, R1 and R2 are both 100K. That gives us an output voltage V out of 5 volts. It just splits it in half. But let's look at Ohm's law here. So we got an input voltage of 10 volts and a whole loop current here of 200K. And that gives us a current of 50 microamps. So not a whole lot, nothing. If you're going for ultra low power, yeah, you're going to want to cut that down, but generally that's going to be fine. No one's going to worry about that too much. But if we drop R1 and R2 to just 1 ohm apiece, V out is still going to be 5 volts, but the amount of current flowing through this loop, independent of what V out is consuming, if it's just not connected, we're going to draw 5 amps, which is insane. You're going to blow something up. It's not going to work. So it's something to be cognizant of. Something to remember is how you size R1 and R2. In general rule of thumb, definitely not a hard and fast rule. There's reasons to break it. But generally, when you're designing voltage dividers, you're going to want them in the hundreds of K when you add R1 and R2 together. So 100K up to a meg is the general area you're wanting to shoot for. In conclusion, you've now learned how to solve voltage divider problems. You've learned that voltage dividers are high impedance outputs and only need to be connected to high impedance inputs. You've got to size your resistors appropriately so that you minimize the amount of current that your voltage divider is consuming. I hope you found this video useful. If you liked it, please give it a like. If you have any questions, please drop it in the comments below. Thank you. Have a great day.